One of those setups that seemingly everyone does at one point in Houdini is this weirdly moving FEM softbody creature. And with the introduction of a new constraint type in Houdini 17.5, I think those kind of weirdly moving creatures are easily doable in Vellum too, with the advantage that they're kind of quicker than FEM. So let's have a look at how to do this. In Houdini, I'll start by dropping down a box, which will be my simulation geometry. And I will scale this along the z-axis to be maybe 6 units long. And also I'll set the primitive type to a polygonal mesh and increase the axis subdivision along the z-axis to be 6 times 4. That's 24. So I have a uniform mesh here. Next, I'll drop down the Vellum configure tetrahedral softbody, which will create 3 nodes, a solid conform, to convert my box model into a tetrahedral mesh, and then a distance, and a Vellum tetrahedral volume constraint. So after this chain of nodes, I'll have a tetrahedral volume with all those constraints set up for Vellum simulation. Let's just uncheck the grid display here. What I want to attach directly after that is another Vellum constraint. Just wire this in here like that, and then set the constraint type to tetrahedral fiber. So what does tetrahedral fiber do? It drives the contraction of those tetrahedral constraints we just created for our tetrahedral volume. But it drives those to contract only along one singular axis, while still trying to maintain the tetrahedral's volumes. What does that mean? In my opinion, this constraint was implemented for muscle systems. So when you look at a biceps, for example, if you move your arm upwards, you can see your biceps contracts. However, as it contracts, the muscle still needs to keep its volume, so it bulges out. That's what basically bodybuilders do when they want to show off their muscles. And the fiber constraints works in a similar way as muscular fibers. So it basically contracts in one direction, and as it has to keep its volume, it expands in other directions. And you can drive the behavior of these contractions with the stiffness for these tetrahedral fiber constraints. So let's output them in an individual group, call this one fiber, and set its stiffness to 0 for now. The bigger the stiffness, the stronger the contraction. And by default, the axis of contraction is the z-axis. However, when we click on the help symbol here, open up our help and scroll down to the tetrahedral fiber constraint, you can see by setting the material W attribute, which is a vector, and it's a point attribute. By setting this vector, we can drive in which direction the tetrahedrons contract. For now, I want to leave it at default settings, so it's contracting along the z-axis, this axis here. Let's attach a Vellum solver down here. Highlight it, let's check the ground plane and just move it down to, say, minus 0.6. Also, let's dial back the constraints durations to, say, 50. Maybe save this, check real-time toggle, and maybe just simulate it. And we can see nothing really happening here. Soft body behavior, which is damped, but we're seeing no contraction. That is because we didn't animate the stiffness here. So let's reset that and increase the stiffness to, say, 10. We can see now the whole contraption, the whole soft body contracts while expanding a bit in the other axis to keep its volume. To get this weirdly walk-in behavior out of this, what I want to do is, on the one hand, I want to increase the friction on those endpoints here, and also their weight, so that they stick better to the ground plane than the rest of a soft body. And then I want to animate this together and in sync with the contraction stiffness here of the fiber. So let's reset that to 0 and group a few points here, which goes in between the box and the solid conform here. Drop down a group node, set it to points, call this one end1, uncheck the base group and check keep in bounding regions, wire this in here, highlight it, and then let's maybe increase the size of this bounding box and move it to one end. Copy this, call the group in this node end2, and it goes on with positive z-axis like these. So I have those 2 end groups, end1 and end2, which I'll use to set up a few point attributes using a point wrangle. First thing I want to set up is the friction, which by default should be something really small, so maybe 0.0001. I want to set up the mass. Let's set its default mass to 0.1 for now. And also, if I want to do that, I could set my material W attribute, a vector, to something other than 0, 0, and 1 as it is by default, but we'll do that later, so let's just comment this out. Now for our initial frame, I want to set the mass of our endpoints a bit higher, so let's just copy this point wrangle here, wire it down here below, delete the friction attribute, and set the mass to, say, 10.0, and have it only applied to the end1 and end2 group. Now to set up our animation, let's dive into the Vellum solver, and I want to use a GeoWrangle here, which I'll set up to work on the constraint geometry by binding it to the constraint geometry here. And then I want to have this run over primitives and drive the stiffness of our fiber group. Let's set it to 1.0 for now. Just check if that worked. And yes, it contracts a bit. So I want to have this in a repetitive motion. And as I'm pretty lazy when it comes to keyframing, I'd rather do this with a formula. So for example, I could use a sine wave. And I know most of you have seen a sine wave, but just for completeness sake, that's what a sine wave looks like when it's graphed out. And instead of x, I want to use my frame number here. So I'll use the sine of my frame. But that would be a bit too hectic, so let's multiply it by 0.2, so basically only 1/5 of the original frequency. Again, when you graph this out, you can see the sine wave is now really stretched out. Oh, a bit too much. Yeah, like this. So my sine wave is stretched out now, and also is going into negative values here, which I don't want, because negative values in my stiffness will break my simulation. So I could do different things here. I could add 1, so it's only going between 2 and 0. I could take the absolute value, which would do something like this. So it'd have those kind of jumps in here. Or in my case, what I want to do is I just want to clamp it. So values can only range between 0 and 1, and anything that goes below 0 is just cut off at 0. So I basically have now a sine function without the negative values, only with the positive values. And let's multiply it by, say, 20. So my stiffness for my fibers will be in the range between 0 and 20. Let's just save this, and let's check. So yeah, I have this pulsating, wiggly worm there. Also, what I can do in here is add some value to just shift my whole function. For example, I can add pi to basically shift it around. Let's just demonstrate that. So by adding some value down here, I can shift my whole function along this axis here. In my case, what worked well is adding pi times 0.75. And again, all these values in here, so offsetting this or multiplying this for the frequency, those just came out of loads of tweaking after I built the setup. And they kind of seem to work for me. So that's my stiffness animation. And now I also want to animate my friction. So only one end has a high friction and the other end has a very low friction. And I want to animate this in sync with the mass. So basically we have only one end with a heavy mass, with a big mass, and a big friction value. So that's basically grabbing onto the surface, while the other one is released. Let's do that with a pop wrangle, which we'll set to the end 1 group. And I'll just copy this expression from my fiber constraints here and put it up here. But I want to drive the friction of that point, and I don't want to have this offset here. So again, frequency is multiplied by 0.2, ranging between 0 and 1. And let's multiply this friction value by something really big, so it should be between 0 and, say, 1,000,000. Let's just copy this, paste it one more time. I want to do the same thing for the mass. However, the mass should only vary between, say, 0 and 10. And if the mass is 0, a point is deactivated for simulation. So we never want this to be actually 0. So let's put something really small in here, which then gets multiplied by this 10. So in the end, our mass value will range between 0.1 and 10. So that's for the one end. Let's just copy this whole pop wrangle here, paste it down there, and let's set the group to N2. That's the other end. I want to have one end released, so low friction, low mass values, while the other one has high friction and mass values. And we can do that by shifting our sine just half of its frequency, which is pi. So we'll just add to this, just shifting the whole function along its x-axis. All right, let's just save this, keep our fingers crossed, and resimulate. And we're getting this weirdly moving creature that awkwardly moves out of frame. However, when I look at this, it bounces a bit too much for my taste. So let's fix that by going up one level. And in our vellum distance constraint, let's set the damping ratio for stretch to 0.1. Do the same thing for our tetrahedral volume here, and leave our fiber constraint as is. Yeah, I like that a bit better. Alright, but this is really low res, and it kind of looks awkward at points where here polygon resolution clearly isn't up to par for what we need for rendering. So usually what you do in simulation is you're not rendering your simulation geometry. What you do is you take a high-res geometry. For example, in our case, let's take a tube along the z-axis. Let's just ghost this. Scale the radius back to 0.5, but the height to, say, 6. let's close this box here and highlight the tube actually so we can see what we're doing. Zoom in a bit and set the tube's primitive type to polygon. Let's increase the columns to say 36 and the rows to maybe 8. Or nah, let's make them high res too, 36, and maybe bevel the edges a bit here, which we need end caps, then bevel the thing. Just check ignore flat angles with a flatness angle of say 22. Then set the shape to round, maybe 6 or 8 divisions, and then increase our beveling distance, say maybe 0.15, like this. So this is the geometry which we'd like to drive with this coarse simulation geometry. And for that we'll use a point deform, and we want to deform our beveled tube, which goes in the first slot. And then we need our rest position mesh, which is this. This is what we feed into the simulation. So this goes into the middle port, and then finally, the result of a simulation goes into the third port here. And when we highlight our point deform now, we can see that's our beveled tube here, and it's being deformed with our simulation. However, that looks a bit coarse at those areas here, especially in those situations. And you can dial it in the point deform by, for example, increasing point capture radius, like this. And now we're getting a bit smoother transforms here, like so. And now if we leave this running, we're getting this weird, awkward creature that's trying to push itself along the screen. And that's basically cheap FEM soft body locomotion using vellum. Really good for awkward, worm-like motions. Again, this is just the basics of it. All we did here was set up a tetrahedral fiber constraint after a vellum tetrahedral soft body, and then within the vellum solver, using 3 wrangles, a bit of math, basically just a sine function, which we shifted around a bit and scale a bit to drive the behavior of those ends and of the contraction. And by the way, we can visualize what these ends are doing by just dropping down a color, wiring the vellum simulation geometry in here, highlighting it, and we'd like to visualize a ram from attribute. Let's use the friction attribute, which should be in the range of 0 and 1,000,000, like this. And you can see we're seeing our attribute here and how it changes. And that's basically what I did to dial in those sine functions and their offsets. So this is just a really, really basic setup. I think the tetrahedral soft body, especially in conjunction with the tetrahedral fiber, has lots of potential for organic movement system, for muscular systems. So I hope you guys build on this and expand the setup. And as always, I love to see what you guys come up with. So if there's any intriguing setup you build with that, please let us know. We're really, really glad to see your guys' creations. So that's it for now. Awkward soft body motion using vellum. So have fun and see you next time.